I hope it's okay to record for this occasion for everyone. So a very warm welcome to the second occasion of the seminar series from B-CRATOS project. B-CRATOS is a future emerging technology FET open initiative that European Union has, and we got funding from that initiative from the old, let's say, the one initiative that has finished just last year or the year before. It was the Horizon 2020. Now it's Horizon Europe, right? So it was the last FET open call in Horizon 2020. And we are very happy and very enthusiastic consortium in B-CRATOS. And okay, the idea for me being here is to give you a small overview about B-CRATOS. B-CRATOS is a project that envisions the connection between brain and machine or brain and organ, and make that connection wireless, so that you're not dependent on tethers, so that you could communicate between the brain and a different entity. It can be a machine, it can be the internet itself, or it can be another organ on the same person's body, right? So B-CRATOS as a project encompasses different technological aspects, and one of the technological aspect is wireless data transfer, and this is what our eminent researchers are going to talk to you about, to give the seminars about. Then other aspects are the state-of-the-art electrodes or implants that can read into brain data. Then we also have an extension of the wireless communication through the body, which is called fat end-body communication, wireless backscattering, beyond state-of-the-art dexterous mechanical hand, skin, which is artificial skin, bio-inspired skin that could have a similar sensing capacity as human skin. Right, so as you might have understood by now that there are different technologies involved in this project. We have had a seminar on the brain interface, which was basically about the electrodes that are used to pick up the data. So that was the first session in this seminar series, and then the second session is focused on wireless data transfer from the brain. So here I have Dr. Pritam Bose and Dr. Ali Khaleghi. So Pritam would give you the first seminar, and to give you a small background about Pritam. So Pritam comes from NTNU, and he had worked in several reputable labs during his PhD days and postdoc, and he's a Marie Curie Individual Fellow, which is a prestigious grant across Europe. So Pritam, without further ado, I would like to invite you to give your presentation. Floor is yours, Pritam.
Can you guys hear me? Yeah, okay. So thanks a lot, Robin, for this kind introduction. So a very good morning to all from the people in US, and a very good afternoon to all the people from Europe. So let me first share my screen, just a second. Can you all see my screen?
Yes, perfect.
Yeah, okay. So the topic of today's presentation is wireless communication and power transfer for implantable medical devices. My talk is going to be a simple one because I'm going to talk about basics of in-body communication system and wireless power transfer. And I suppose Ali is going to dwell into much more deeper stuff. So my entire talk will be divided into three broad parts. So initially, I'm going to talk about wireless communication and some of the basic in-body wireless communication system methods. And then I'm going to talk about wireless power transfer, and particularly for implantable devices. And then we are going to see that maybe we can actually approach both this field in the same way and try to come up with something called joint wireless communication and power transfer. But before talking about, just to limit the scope of this talk, I'm just going to talk about in-body communication system and limit my talk into system design of in-body communication systems. But before talking about different in-body communication system, let's try to talk a bit about wireless implantable devices and try to see that why is it so important in the recent times. So I hope that most of us have heard about wireless implantable devices because it is quite popular in the recent times. And there are mainly two reasons for that. First of all, they have shown their promise in treating several critical medical conditions. And due to the improvement in the current electronic technology, now it is possible to design really small implants with high battery life. So these are important innovations in this field. So here I have listed down few of the common implantable medical devices. For example, on the top left, you can see these deep brain neurostimulators. So it is used for assisting patients with neurodegenerative diseases like Alzheimer's and Parkinson's. And then we have cochlear implants that are used for treating patients with hearing disabilities. And then we have gastric stimulators that help patients with gastric disorders. Sorry, is there any comment or question? Okay, so then we have the most popular kind of implants. Those are the cardiac implants. So cardiac implants can be categorized into three broad categories. For example, we have pacemakers, and then we have ICD devices, and then we have CRT devices. And then we also have other different kind of implants. For example, we have the foot implants, and we also have insulin pumps. Insulin pumps are normally used for patients with diabetes. So these devices are implanted inside the human body, but they need to communicate with the outside world, isn't it? Because the doctors need to get the data from these devices so that they can analyze the health of the patients. And maybe they also need to make some changes in the configuration of the devices based on the health of the patient. So that's why designing in-body communication system for this kind of devices is quite important. And there can be another case as well. So there can be multiple implants inside the body, and these devices need to communicate with each other, maybe to work in a synchronized way. Let me give you a small case study here. So my PhD and postdoc work has been mainly focused on something called multi-node leadless pacemaker, particularly for the cardiac application. So where we had multiple capsules in different chambers of the heart, and they need to talk to each other continuously to work in a synchronized way. So that's why developing communication system for this kind of application is really important. But I hope that by now you have already understood that designing this kind of in-body communication system is not easy, because in free space, you have a lot more freedom. So you can do some analysis, you can develop the system, and you can test it over and over again until you get what you want. But for in-body communication system, it is kind of difficult because you cannot just grab a person and ask him like, can we put some devices in your body and test it? That is not possible. So that's why people have come up with different methods to do that, starting from simulations of human body models, mainly voxel models, and then doing phantom experiments. So phantom are actually simple chemical solutions that mimics the properties of human tissues. And then people have also done extensive animal experiments, mainly on pigs and dogs. So let me just talk about few in-body communication methods here. So these are the most popular ones. So here you can see that this is the most popular one, which is called radio frequency communication. Because here we can get the knowledge from the free space, because people have done years of work in free space. So here this uses microwave for communication. And then there are also standards available. I think it was around 2010 or 12, the standards came out. So it is in IEEE 802.15.6, I suppose. And they have listed out the frequencies that can be used for our purpose. For example, they have listed out this band of 402 to 405 megahertz, which is called the mixed band, which stands for Medical Implantable Communication System band, that can be used for the implants. And then they have also listed out other bands that can be used. For example, this industrial, scientific, and medical band can also be used. So this is a free unlicensed band that can be used for medical purposes. And I suppose the frequency range is around 434 megahertz, 868 megahertz, around 2.4 gigahertz. And then there is also ultra wideband frequency that can also be used. So here I've shown you a simple simulation that we have done. So we have actually put a capsule inside one of the chambers of the human heart. So here you can see the lateral side of the body. And then we try to send some signal from this device. And here in this colorful diagram, you can see that these are kind of the strength of the signal. So red being the highest and blue being the lowest. So you can see that the strength of the signal falls very rapidly. So the attenuation of the signal is quite high inside the human body. So human body is a lossy medium that attenuates the RF signal. So one of the thing is that this RF communication can be used for deep implants. So this is one of the advantage of this RF communication. And another thing is that this RF communication is a wide range. So we can start from few megahertz and go up to gigahertz. But there is also another problem that these parameters depend a lot on the frequency that you are using. So if we go up in frequency, the path loss or the attenuation inside the human body increases. But if we go up in frequency, the size of the antenna decreases. So that's why there is a trade-off between these two. So it depends on the size of the device also, which we want to implant inside the body. And as I mentioned that it consumes a lot of power because this RF system, they have antennas and a lot of electronics. So that's why power consumption is quite high in this kind of system. So in all of these communication systems that I'm going to talk about, so I'm going to talk about some of the pros and some of the cons of these methods. Moving on, we have inductive coupling. So inductive coupling uses magnetic coupling for communication. And the architecture is really simple because they use coils, magnetic coils for communication. And they can also be used for wireless power transfer. But the problem is that they have really short bandwidth. So they are not applicable for applications that require really high data rate and a large bandwidth. So let me give you a small example here. For example, we have an application called Capsule Endoscopy, in which a capsule is swallowed and it monitors the gastrointestinal tract of the body. And the goal is that this device will be able to automatically send data or video outside that the doctors can analyze and do some monitoring of the patient at the go. So for this kind of devices, we need really good quality videos so that the doctors can analyze the data. And that's why we need high data rate. So maybe inductive coupling is not a good option for this kind of systems. And they also have short range. And then we have something called human body communication. So this is also known as intra-body communication. And then there are two types of human body communication. One is capacitive coupling and another one is galvanic coupling. So capacitive coupling is the original method that was invented by this guy called Zimmerman. So this human body communication, they use human body as a communication media. So they use electrical signals that flows through the human body, so the tissues of the body. So in this capacitive coupling, we have a common ground, so the current flows through the common ground. But in galvanic coupling, both the transmitter and the other device, they have two set of electrodes, so there is no common ground. So all the signal flows to the body. So, but the main problem of this kind of system is that the results vary based on what kind of tissue this implant is placed, whether it is a muscle or a fat tissue or any other kind of tissue. And the range is also quite short. And the other problem is that the results have varied a lot between different groups. So people have worked a lot on this system, but results have varied between different group, and then there are also no standards available. So one thing I actually forgot to mention about this inductive coupling. So one of the main problem of inductive coupling is also the alignment of the coils, because for good communication, the coils inside the human body needs to be aligned, because if there is small misalignment of the coil, then the communication is not good. So this is also another major problem of inductive coupling. Moving on, we can also have ultrasound communication that uses ultrasound signal for communication, and it has really low attenuation and low power. But the main problem is that if this implant is placed behind the bones, then there can be no communication because all the signal is reflected by the bone, and the data rate is also not that high. And then we can also have optical communication, which uses infrared signal for communication. We can have really high data rate, and the size of the implants can also be made really small, but this is not suitable for deep implants. So this is only good for superficial implants, like the implants that are placed just under the skin. So this is the last communication method I'm going to talk about. So it is called molecular communication. It is the latest form of communication, and the field developed around 10 years back. So this is a biological form of communication in which the information is encoded in the ions or molecules, and then these molecules are used for communication. So you can see that it is a biocompatible form of communication because the ions inside the human body is used for communication, and it also has really less power consumption compared to all the other methods. But since this is quite a new field, so there has been limited work on this field, and there are really few groups in the world that are working on this. So for example, Dr. Ali and Professor Ilanko's group is working actively on this, but the results have mainly been theoretical work. So there has not been practical implementation of this kind of work because it is kind of difficult, because there is limited expertise in this field to do practical work, and practical implementation is also not that easy. So moving on, so selection of the good communication method is of course important to improve the lifetime of these implantable devices, because longevity of this implantable device is one of the most important factor in the design of this kind of implants, because you won't want a device that will be placed inside the human body and you have to change it every year. That is not feasible, because normally the implants are placed using surgery or using catheter technology. So that's why the goal would be to have an implant that will have a really long lifetime. Maybe the optimum goal would be to have it for your entire life. So that's why selecting the optimum communication method is not enough, and we need to have some kind of wireless power transfer to improve the lifetime of these devices. So here I have shown some of the methods for wireless power transfer: inductive coupling, magnetic resonant coupling, and then EM, electromagnetic coupling. So this uses RF signal for wireless power transfer. So here I've shown some of the common things that we use in our day-to-day life. In this talk, I'm mainly going to focus on this RF wireless power transfer, because we are going to see that this has some of the advantages over the other methods. And at the end of the talk, we are also going to see that how this can be linked, like how this RF communication and RF wireless power transfer can be linked to do something together. So microwave enabled wireless power transfer was introduced by Tesla, but he did not do much work on it because he ran into financial troubles. And I think he actually started this work around 1914. And then this field was enhanced by the invention of something called rectenna, which stands for rectifier antenna, that actually converts this radio frequency signal into DC current. Now let's try to see some of the advantages of this RF-based wireless power transfer. So one of the main advantages is that the power can be sent over a large distance. So this is quite applicable in free space, because we can send power over a very long distance, like many kilometers. But how is it important for these implantable devices? Because till now I've been talking about that we have deep implants, but deep implants is placed deep inside the human body. But then the depth is not that high, because from the surface of the body, it will be around 15-20 centimeters, not more than that, or maybe a bit more. So this is not a really high distance, but then why am I calling it deep implants? because the attenuation inside the human body is quite high. So a depth of 15-20 centimeter is quite high compared to the distance. So because the signal loss is very high inside the human body. So that's why RF communication could be a good thing to power these implants that are placed inside the human body. And then there can be one to many wireless power transfer. For example, a device from outside can be used to power many implants inside the body. And it can be many to one as well. For example, many devices can be used to power only one device. And then the power level can be controlled. So let me talk a bit about this. So I've been saying that the attenuation inside the human body is quite high. So if we send low power, then we might not be able to get something to charge these devices inside the body. But what if we increase the power? We can increase the power indefinitely. Then of course we are going to send some power and we'll be able to charge these implants. But somehow this is not possible because we have something called Sar value. So Sar stands for specific absorption rate. So which is the threshold value that has been set by the standard. So we need to send the power below this threshold, because otherwise we will cause heating of the tissues and damage of the tissues and even maybe kill the person. So that's why we cannot send indefinite power. We can only send power that is below a threshold value. So that's why we have several constraints here. And then this power can also be controlled based on the number of antennas. So maybe we can also use an antenna array, and we can do a lot of different things. And this can also, so we can also use ambient RF signal for charging this implant. So we have a lot of ambient RF signal. For example, RF is used for mobile telephony as well as Wi-Fi and all other different purposes. And then the main problem is that the power received is quite low if we send it below the Sar value. So this is one of the problems. So before I talk about, so now let's try to see that if we can try to combine this wireless power transfer and wireless communication to come up with something together. But before talking about that, let me give you a small analogy here. So in cellular communication, when we talk over phone, a signal goes from your phone to the base station and from the base station to the other user. So this signal actually carries the information that we want to send. So it can be voice signal, it can be data, anything. As a matter of fact, this signal not only carries information, but it also carries energy. And if we can harvest both the data and the energy at the same time, then the battery of your phone will be charged automatically while you're talking. This is quite interesting. So, but unfortunately, not much work has been done in this field because a lot of work has been done in communication theory, and people have also worked a lot on this wireless power transfer. So these communication theories, they have made a lot of progress in this domain, and then this wireless power transfer has also been done. But this is a field that actually came up in 2008, like around 14 years back. And this field was introduced by this Professor Lavar Boschny from University of Illinois, Urbana-Champaign, where I'm currently based. So he actually introduced a information theoretic paper on this. And he showed that it is possible to do simultaneous wireless information and power transfer, in which we can harvest both the data and the power at the same time. And that's why this can also be applied to implantable devices. So this is called in-short sweep. So here I've listed down few of these sweep methods. So for example, we have this integrated sweep, which is the original version of the sweep, in which we can send both data and power over the same signal. And then we can also have this closed loop sweep, in which data is sent in one direction and power in another direction. And then we can also have decoupled sweep, in which we have two sets of devices, in which the information is set between one set of devices and the power between another set of devices. And now let's see how this can be used for implantable devices as well. So for example, we have an implant inside our body, and then there is a device from outside that is trying to communicate with this device. So then this device sends a communication signal. What we can do some power splitting. So there can be one system that actually decodes the information, and then there can be another system that harvest the energy. So there can be different methods for doing that. For example, we can also have time division method in which we send power over a signal, and then in another time instant we send data. And then there can be other system as well. For example, if there is a network of implants inside our body. So I gave you a case study before in which we had this multi-node leadless pacemaker in which we have multiple implants inside different chambers of the heart, and they need to talk to each other in a synchronized way. So they need to have frequent communication between them. What will happen if this communication signal can be used for both data and energy harvest? So then we can improve the lifetime of the small capsules, because then these capsules will be able to charge from the communication signal that is sent between them, as well as it can also be charged from the communication signal that is sent from the outside. And even we can have this ambient communication signal that can be used to charge these devices. So this is the main goal of our work. So this is a very new field because there has been no work in this field for using this simultaneous wireless information and power transfer for medical implants. And then there is a lot of scope to work in this field. So starting from information theoretic model to system and signal design, as well as designing or practical design of the entire system. So this can be done. And as I said, that there hasn't been any work on this, so I might not be able to say a lot about this, but I think this is a field that is going to come in the future, because in 6D, this is an important task group, because there is a task group which is actually working on this joint wireless information and power transfer. And they are also working on this joint communication and sensing, in which the same communication signal will be used for data transfer as well as sensing. So this can become an active field in the future. So I think I'm running out of time, so I will just try to wrap up. So we all know that we have a lot of medical wearable devices now. For example, our watch, they can monitor our heartbeat, they can do ECG, as well as they can measure our blood pressure and do a lot of things. And in the future, we'll be having a lot more wearable devices. And then there will be also implants in our body. So these implants and the wearable devices, they can communicate directly with the cow, maybe in the future, and then they can form this Internet of Medical Things as well as Internet of Implants. And then this entire communication that can be used for both data transfer as well as wireless power transfer. And then we might be able to charge these devices automatically. So maybe in the future, then these devices need not to be changed. And then there could be also batteryless implants in the future, the implants that will stay in our body for a lifetime. So with this, I'm going to end my talk here and pass on the baton to Ali. So thanks a lot for your attention, and please feel free to ask me questions whenever you want. So now or later, whatever you prefer. Yeah. So thanks, guys.
Thank you. Thank you very much, Pritam, for your very interesting, fascinating talk. If there is any questions, we can take 5 minutes for Q&A sessions.
May I ask a question?
Yes, please.
Definitely. Yes.
First of all, thank you for the wonderful talk. I wonder, what is your opinion on irradiation-based power transfer, like with IR irradiation, red light irradiation? Do you have an opinion on that?
Yes, so that is also a interesting field, but for deep implants, it is kind of difficult because there is huge attenuation inside the human body. So in free space, things are much more simpler, because in free space, you have a lot more freedom. And then if there is no obstacle, you can actually try different kind of wireless power transfer methods. But for human body, one of the main problem is that there is huge attenuation of signals inside the body. And the other problem is also the power limit, because there is a Sar value and you cannot go above this Sar value. So there are several constraints in this kind of system. And the other problem is also that there is, so if this device is placed beneath the organ, maybe we won't be able to reach it, because then the entire system will be blocked by the organs or other different kind of tissues. So that's why there are a lot of constraints. But of course, we cannot rule out any field, because maybe this field will come out in the future that can show that this wireless power transfer can be done. So of course, we can rule out any options.
Thank you. Thanks
Yeah.
for the invite.
Thanks, John.
Right. We have another question from, is it a question? Mauricio?
Is it in the chat?
Yes, thank you, Pritam, for this very interesting presentation. My question is regarding inductive coupling. I have 2 points here. First, you mentioned that about the short range. How short is the range compared with the other methodologies, and also regarding the fact that the body is known as a non-magnetic medium, how it is the relation with loss with respect to the other approaches? In that, what do you have managed to come across regarding that approach?
Yeah, so first of all, I want to mention that I'm not a guy who is actively working in inductive coupling, but based on the knowledge that I have, I think that this inductive coupling, the main problem is, as I said, is the data rate, because for this capsule endoscopy application that I said, for that, we need really high data rate to send videos outside. And this inductive coupling may not be a good option for that, but maybe for other application, for example, a device that is placed that doesn't need that high data rate, maybe it could be a good application. For example, for this CRT devices that are placed just under the skin, so maybe that could be a good application. But I actually forgot the last part of the question that you asked. So can you just say it once more? So I could not recall.
About the non-magnetic nature of the body, because with other methods, we have that the body is very lossy dielectric, but from the magnetic point of view, it is almost the same affair.
Yeah.
So from that point of view, there should be some, so we say, convenience. But I'm not even no expert at all on that. I'm just, maybe you have come across something on that.
Yes, definitely. So for this inductive coupling, the loss is quite less. So yeah, so body being a non-magnetic medium, so the loss is quite less. So that's why like this inductive coupling is used for different kind of methods. So it is used for different methods for communication, but I don't think it is that appropriate for this high data rate application, but it can be applicable for low data rate applications. And I think Ali is actively working in this field, so maybe he's the best guy to comment on this.
Yeah, Pritam, there is also a connected remark in the chat. Probably you have already read about bandwidth of inductive coupling and the possibility of higher data rate. So maybe after Ali's talk, maybe we can have a discussion on that. So yes. Thank you very much, Pritam, for your nice presentation. So let's move on to Ali's presentation. So Ali is a senior scientist from NTNU, and he's also a co-PI in the B-CRATOS project. Ali, your talk will be on ultra-low power wireless communication for implants. Floor is yours, Ali. You're welcome.
Yes. Hello, everyone. Can you see my screen?
Yes.
Okay, great. Thank you for the introduction, and the talk that given by Pritam almost complete the background. So I'm going to talk here about ultra low power wireless communication for medical implants. So the reason that we need ultra low power, so as Pritam mentioned, always we have limitation with powering the devices, and the longevity of the implant device is very important to support the implant operation for a long time. So it's very important to come up with a solution that implant power consumption reduces. So other methods of the power harvesting, like power harvesting from the movements and different sources, can be efficiently used to power to run the implant. So based on that, I'm going to present. Okay. I will talk about the essential needs of the implementing wireless technology with the medical implants. I will introduce the wireless communication methods for implant medical devices, including the high efficient methods for communication. Then the feasibility of using new methods like battery-free communication for wireless capsule endoscope, and also for cardiac pacemakers as a pilot study will be discussed here. And at the end, I will talk about the NTNU role for supporting brain-machine interface in the B-CRATOS project. Okay, in this figure, you see a person empowered by multiple implant devices in different organs that can collect the health information and communicate the data to a network to use the network capacity for early detection and treatment of possible disorders. If such system can be developed, it would revolutionize the future of the medicine. There are different variety of electrical. So now what is needed? There are some sensor technology that has already been developed, and there are different variety of electrical, optical, chemical, and mechanical sensors that can be used to collect the biological signs. But these sensors can be implanted. Yeah, these sensors can be implanted by surgery or injected into different organs, such as brain, gut, heart, liver, to collect the local biological information on demand. Some of the sensory data might be very life critical. The information exchange and communication of the information among multiple sensors or similar sensors in a specific organ is very needed to validate the collected data. Also to make trust on the data and detect possible faults. The sensors has very limited capacity to process the data since they are battery powered or can harvest a very slight energy from the environment, like the cardiac devices can harvest the energy from the cardiac heart beats. Providing wireless communication capacity to the sensors can shift this sensing capacity to higher level, in which the sensors can be connected to the powerful network that can be present in the body area or in the big network like 5G or 6G. So if we do such connection between the implants and connection of the implants to the on-body devices and to the network, we can use the capacity of the network for computations, data storage. We can apply the machine learning algorithms and use some AI models for early detection and providing some effective treatment plans for the people. So that's the future of medicine that I think is important that we look in this direction. But to realize such a system, we need some important steps to proceed. One of these steps is the communication system. Without communication, none of these sensors and implants can interrogate with each other or transmit and share their information with network. So then we need to find a new communication paradigm that bring this capacity to the implant without adding any additional power consumption, complexity, electronics. That's the goal. That's the wish. So as Pritam also focused, there are different communication technologies that can be used. And one of these that is well established is the IF technology. The use of IF for implant is not so efficient, as Pritam also mentioned, because the human body is lossy medium for radio signals. So, and also the electronics that is needed to generate radio signals for communication from implant to external, they are also very power consuming electronics. Even if you use ultra low power devices to make high frequency and radio frequency oscillations, you need significant power. Other part is the antenna. That is a part of the communication system. And usually the implants are very tiny and small. So we know from the antenna theory that if the antenna size compared to the wavelengths is quite small, the radiation efficiency drops very fast. But on the other side, if we increase the frequency, more loss in the biological tissues stops the communication. So there is a problem in this field. Recently, human body communication is considered for by using low frequency signals, and it uses the conductivity of the biological tissues, and the physical medium is used as a means for communication. This is not possible in free space, but for our body, while we have our body is like a conductor, we have the ions, it's lossy conductor. So it has some ions that can convey the information. Again, in this case, since we are using radio signal or high frequency or low frequency signal, the antenna is a part of this system. And since the frequency should be low to save the energy, electronic circuits energy, the antenna efficiency drops a lot. And then again, we have very challenge for communicating in distance. Other problem is that if we want to communicate from implant to on-body, our skin and the fat are somehow high impedance to the low frequency. So they hinder the communication. Human body communication or conductive communication might be good for inside to implant connections, but it might have some problems for implant to on-body. There are other ways of communications that I listed in these 3 figures that I will focus on these topics. So one is by using the backscatter communication. Backscatter communication is a method that uses radar approach, in which radio signal is sent from external body toward the implant. And then the implant just make changes and alters the amplitude and phase of the radiation by that is controlled by the data source. And then the reflections can be picked up externally. In this way, the implant system will not have extra circuits for communication, no electronics for IF generation, and also a MEMS switch, very low mechanical switch can be used to alter the antenna impedance. The other way is by using conductive impulse that we have shown the feasibility for implant-to-implant communication. This is similar to the human body communication where the low frequency signal is used, but here we use impulse signal, which is like baseband impulse from very low in frequency, several hertz, up to maybe 1 megahertz or less. By this way, we limit the transmitted power to single pulse. And also the electronics that is used in this system is quite light. And in this way, we can convey like low data rate information in the orders of hundreds of bits, but very low power of order of tens of picowatt per bit. The other way around is by using molecules that can show very low data rate, but it's based on the material transmission. And also it's not very well established field. There are not so many devices developed in this area to do the experiments. And it's based on mainly diffusion of some molecules and reception of these molecules in the target. But in biology, this is done naturally, where cells release some particles known as exosome, and some target cells can receive these particles, and that will be simulated like a communication system. So here I give a table, maybe later in the webinar you can check this table. If you see this backscatter communication that I introduced, the power consumption of this system for a data weight of order 30 megabit per second is in the order of nanowatt. This is for the implant side, where we don't have enough power, but again, the complexity is external to the body. Maybe in future, this backscatter communication can be applied by the picocells in the cellular network. Some part of the energy can be reflected from the implant that can be picked up by the local network. So the implants can be directly connected to the large networks. That's our wish. So the energy resource for the implants are the main limitations. So we expect that an implant can last for 5 to 20 years without charging or changing the battery. That's what is also some limitations applied by the regulations, by the medical regulations, to do not change the implants so regularly. Battery capacity is limited because of the technology, and also it's difficult to harvest the energy from the local energy. For example, it's possible to harvest some energy by from the organs that has natural movements like the cardiac, like the heart. But again, the system should consume very low power to use this energy for a long time. If we add this active communication to the implant, it will be quite difficult and it will deplete the battery. Some other technologies are also used, such as used to harvest the energy, such as blood perfusion and use of glucose and ATPs to get the energy from the cell's environment. Wireless charging is also another approach that can be used, like the magnetic coupling, as mentioned. That's more efficient, but for superficial implants. And when the implant goes much in deep, the efficiency reduces. But again, integration of these coils and these coils in the implant consumes quite large space and reduce the efficiency, but it's an approach. So the other limiting factor with the implant is the size of the implant. That should be in the order of from micro size to maximum 5 centimeters in size, and it depends on the use area. So while we have like very tiny implant, integration of all electronics and communication system becomes much more challenging. The other factor is the biocompatibility of the implant. That should be biocompatible. In this case, the metal casing and metal shell is usually used. That limits the integration of RF system, radio systems, and wireless communication systems with the implant. Also, in the implant development, the integration of the electronics cause significant interference that is an engineering challenge that should be considered from the design to implementation, and the electromagnetic compatibility factors should be followed. The device safety, trustability, identity are the other factors, and the device security in communication, safety to remote eavesdroppers for hacking, remote access and control, also reliability are the factors that should be considered for the implants. These all are some challenges, a list of some challenges that must be considered in the implant development. Here are some examples of implants powered by the wireless communication technology is given. Wireless capsule endoscopy and brain-machine interface are examples that need very high data rate. Wireless capsule endoscopy, as you might know, is a device that can be swallowed and contains a camera that makes video of the digestive tract to detect bleeding and also find some polyps that are the cause of colon cancer. Brain-machine interface is a device that can read the brain signals from different parts of the brain, depends on the application. A brain cortex with very wide application in brain research and for human aid. Next example is a cardiac pacemaker that requires low data rate. So the first one needs high data rate, the second one here needs low data rate. The cardiac pacemaker is used to resynchronize the cardiac beats to treat the cardiac arrhythmia. The next technology, the new technology here in this field offers a small capsule that can be guided through the veins to the heart chambers, like right ventricle, right atrium, and communication among the capsules is essential for delivering the therapy, because these capsules should communicate to each other to follow up the same rhythm control inside the heart. Here, low data rate communication between the implants is necessary. Otherwise, it will not operate as planned. So that's a replacement for wire-based pacemakers. Also, there are some other chemical sensors, biochemical sensors that can provide low data stream that can be used here for low data rate communication. Here is an example of wireless capsule endoscopy that we have developed at NTNU and Oslo University Hospital. In this system, we have a capsule with onboard camera and a reader on the body surface. The capsule has no electronics for communication, and we have demonstrated the feasibility of 10 to 30 megabit per second video streaming from the capsule to an on-body device, and then the connectivity of the system to the larger network like 5G that partially has been developed and some part is under development. The aim of this project is to detect the polyps with very low latency, and by using the edge computing capacity in the network and giving feedback to the capsule to control the imaging parameters. Other application that we considered also, and we have demonstrated the feasibility, is for the cardiac pacemaker. On top right, you see a subcutaneous CAN device that is used to remotely communicate with this backscatter communication with two capsules. So in this case, the capsules has no active transmitter. The subcutaneous device can slightly power the devices and get their reflections to collect the sensory information. Then the subcutaneous device can be used to manage this network with two implants. But later, this can be multiple implants in different chambers of the heart. And next goal for us is to miniaturize these implants. Other way, as I mentioned, by using impulse communication, baseband impulse communication, in which you see here the short pulse that is created by this electronics, and it's spread inside the body and can be picked up by the second electrode close inside this heart chamber. So we have shown the feasibility of this technology and also the power consumption for this system, which is also active communication, but it has very simple electronics by using a MEMS switch and a capacitor that discharges the pulses to the medium, and the amount of the power that is consumed is about 10 picowatt per bit. So now in this B-CRATOS project, we are partner, and we are the work package to, we are leading the work package too. Here we are planning to charge the brain implant wirelessly and also provide the sensory data to the brain implant to make stimulation to bring some sensation feeling to the patient. and also pick up and also read the status of this implant, such as temperature and some other critical parameters of the implant. In addition to that, we have to provide the high data rate brain readout to this project in the orders of 30 megabit per second. So the accuracy of extracting the brain patterns in the motor cortex becomes very high, in which the user can have higher capacity to control the bionic arm or devices. So here are some examples. As I mentioned, the powering unit, we are planning to handle around 30 milliwatt power to a device that will be provided by BlackRock Microelectronic. And also we will provide the power to the sensory system in the implant. Also, we will do telemetry and telecommand with the implant, in addition to this high data rate. In this case, the data security, the radiation safety, and reliability for use, because this system should be used 24 hours and 7 days for at least 6 months on an animal experiment. So that's our goal. And in conclusion, it's as I talked, it's very important to provide low power or battery-free communication payload to any implant to develop the future of the Internet of medical devices. So that's very critical, and because of the power limitations in the implant area. So also we have to be able to use the capacity of the larger networks to shift the computations and also calculations of the implant and decisions to external body to limit the power consumption of the implant. Any task that can limit the power consumption of the implant and remove some tasks from the implant is welcomed in this development phase. So finally, the goal is to provide better healthcare and sustainable health system for people. Yes, thank you. This project, B-CRATOS, has been funded by Horizon 2020 under this grant number, and we at IES at NTNU, we are leading this work package number 2. Thank you all for your participation. Yes.
Thank you very much, Ali, for this very informative talk. Floor is open to questions. Mortesa. Sorry, so someone had a question.
No, sorry, I just forgot.
All right, okay, sorry. No problem.
Microphone was on.
Right. Is there any question for Ali?
May I then kick in? It's a bit off the topic, but I saw the headline, data security, and this is what I think most public and in particular data management and data security are worried about when people are interfering with your health data. How do you make sure, or what is your concept to make sure that these data connected to the implants are safe and not misused by external?
Yeah, that's a very good question, because anyway, the implant, as we mentioned, has very limited capacity, right? So we cannot apply very hard codes, encryption, data ciphering or other techniques. So that's a big challenge in this field. One of the approaches is to physically secure the channels. For example, if we use this human body communication that is based on conductivity. So to access the implant, you need to have something in contact with the person. So you might not get the data maybe above 5 centimeters from the person. But when it comes to this backscatter that I mentioned, it's different because the information that you get from the implant is mainly on the surface. There is very less radiation. That's mainly physical. But for sure, in the other levels of the security, like the network addressing and all this, there are a lot of challenges that once this technology is under development, it should be considered. That's important point.
Yeah, absolutely. I agree. And I think the whole community should think about it right from the beginning, because I think this is the main concern we will head into when we go into public. Yeah. At least is my opinion, but I'm a German. Maybe we're a bit weird about this.
Right. Right. Correct.
Thank you.
Yeah, Ali, if I can just comment on what Johannes asked, there is a very tailored or specific call from the European Commission on the cybersecurity issue of connected medical devices. So which is very contextual. So this is an open call, it's going on, and then the Commission is asking for new projects just to improve the security of medical devices. So exact same reason as you were asking. Yeah, so it's a big concern. So we have some questions in the chat. So we have a colleague asking, can we use a solar battery for power?
That's a question. Anyway, if it is something on the body, then you have access to the solar light, so you can use it. But maybe the light cannot penetrate more than maybe half a centimeter or even less, and it has very high attenuation inside the body. So it's difficult to maybe to use something under the skin. It might be possible to get the light to charge, but anyway, the size is also one challenge. Whether the area that you use, because the implants are quite small, whether the area that you use and integrate with the implant is sufficient enough to get useful power.
Thank you, Ali. We have another question in the chat. What is the size of wearable reader in backscatter communication?
Yes, the size, at least the system that we have developed is mainly by using off-the-shelf electronics, and we have not focused to reduce the size. But if it is like integrated circuit design, it can be very, very small. But again, so in the backscatter system, you need to handle more power, because you need to send the power and get it back, and you have a lot of two-way pass loss from external to the implant, and also the implant is quite small. Then the power consumption might be something that might limit the integration in very small space. So you might need sometimes for an implant in 10 centimeter, you might need to transmit about 250 milliwatt. So yeah, the one that we developed is something in the order of 5 by 10 centimeter, but we have not tried to make it smaller. It can be half of this size.
Right. Okay, so yet another question. This is interesting in terms of the network. So would a network of wireless sensors introduce noise or crosstalk between them? If that's so, how do you mitigate that issue?
Yes, for sure. There are always the crosstalk between the sensors. So in some level, you can consider using some compact filters to discriminate this signal crosstalk. Using SAW filters is one approach, surface acoustic wave filters, because they are quite compact. Again, this is a challenge, should be addressed in the development phase. Yes, I think the general terms that is used in other fields can be applied here, but again, the size and the size is the the problem here.
Right, Ali. Thank you. Is there any more questions regarding the topic of the talks? Doesn't seem so. Ali, just one question from my side.
Yes.
What do you think about the compliance of such readers? Are they flat or are they compliant? Or
You mean compliance with the standards?
no, compliant with the human body, let's say. Now we are talking about brain communication, right? So
Yeah, this is something on the body, on the surface. So with like 2 centimeter gap to the skin. So, but when we want to integrate, maybe because of the shape of the head, if we want to integrate it on like a casket kind of device or holder, it should follow the geometry of the surface. So maybe in this case, using flexible electronic flexible PCBs, and yeah, these are some approaches.
great. Thank you, Ali. So let's wrap up the session here. So let's thank our speakers once again, Dr. Pritam Bose and Dr. Ali Khaleghi, for your nice lectures, your insights into the topic. We enjoyed very much, and thank you all for attending. Hopefully see you all in the next webinar. Take care.
Thank you, Robin.
Have a nice evening.
Thank you, Pritam.